Swayam Prabha. Digital India. Educated India.
So today we are going to study some more properties of our random process. Okay, so index could be time, right? So if index is time, then the way we are interpreting random variable x, and then we said my random process x can be thought of t omega. What is this? This is x of t of omega. So if you are going to treat this random process x, as I said, it can be thought of function of two arguments. One argument is the index and other is a sample point. That index could be time itself, in which case it is going to talk about that tth random variable and the value it takes at the sample point omega. For the random process, we have also defined mu x of t. This is, and so this is for all. So recall that this t could be just integers, in which case it is uncountably, it is infinite but still countable, or it could be an interval itself in which it is uncountable. Okay, so and we distinguish these two cases, discrete random process and continuous random process, based on whether my number of elements, the number of indices in t is countable or uncountable. And then we had this question of yeah. So again, there are two discreteness that is coming into picture here, right? One is in terms of the indices, whether indices are taking discrete value or they are taking continuous values. Based on that, we are classifying our random process as either discrete or random process. But each of the random variable in this process itself, they could themselves be discrete or continuous further. So for example, so let's take an example. Okay, let me just first complete this. This is covariances. So let me take a x where my t is equals to z, that is all positive z plus, let's say all 1, 2, 3 up to infinity, and my for t belonging to t, let's say x of t is equals to 1 with probability half, and let's say minus 1 with probability half. So this random process here by our definition it's discrete random process, and further each of the random variables here themselves are discrete. Okay, but now we can say that my xt is let's say Gaussian distributed with some mean t which depends on the index, let's say, and also variance, some variance. Here for each index my distribution is what? Is taking continuous valued outcome. So here, even though it's a discrete random process, but each of my random variable is continuous here, because I know already my Gaussian random variable is continuous. right? So we said that this is a mean function, this is what? Correlation, and this is called covariance. So yesterday in my class I think I made one small error in saying that when these two random variables are the same, we said it is going to be called as further auto covariance or auto correlation, but that's not the correct. The thing is, we are talking about one random process here, right? If you are just talking about one random process, then in general we are going to call, instead of correlation we will also call it as auto correlation and auto covariance. So if we are talking about only one random process and they are defined for this particular random process, so this is auto correlation. The auto is coming here because we are talking about the same random process. In that random process we are looking at the correlation between two random variables. So that is why you can, sometimes it is also called auto correlation. So we will see another notion called cross correlation and cross covariance when we have two different random processes. So that we will come to a bit later. Now for this random process, I want to define one important notion called stationarity. A random process. So what we are saying is, take any random process T and you take any n random variable. So just take n. N is telling, okay, it's telling what is the number of random variables you are interested, and then take any t1, t2, tn. This is going to tell you the indices, which are those random variable you are interested. For any such n and for such any vector, if you are going to look at the joint distribution of these n random variables taken at t1, t2 up to tn, and look at the joint distribution of their shifted versions, that is t1 plus s, t2 plus s and tn plus s. If they have the same distribution, then we are going to call the random process stationary. So what it means in a way is, like, what we are doing is this set of random variables, joint distributions, now we are looking at another set of random variables delayed by time s or shifted by time s. Then if this again have the same distribution, then we are going to call our random process stationary. That means if my random process is shift invariant, whatever, let's say I am looking at, so let's say I have a process where each random variable correspond to one particular day. If you are going to look at the joint distribution of, let's say, day 2, day 5 and day 7, this joint distribution of these three, and then you look at the joint distribution of day 3, day 6 and day 8, that is everybody just shifted by one, the joint distribution of first three will have the same joint distribution of the last three. In that case we are going to call it as stationary. Okay. So what is this basically means is, in terms of CDF functions, this is going to be same as so if you just to shift the time indices for all of them by the same amount, then the joint distribution does not change. Okay, let's now understand what is the meaning of this stationarity. What is the thing that the stationarity implies. Okay, now let's take a second order. So what do you mean by a second order random process? So we say that its second moment is going to be finite for all possible indices, right? If you are going to take a second order random process, okay, now let's apply this definition to n equals to 1. So remember this is for any n, this should happen. Okay, so let's take this n equals to 1 and then apply this definition. Then what it says is f of n equals to x of, let's say x1, let's say x1, and then at some time t1, this should be same as this n is equals to 1 here, this should be same as f of x of n, and then x1, that is t1 plus s, and this should be true for all s, right? Because this should be also true for all s. What is this telling is, you take the random variable at time t1, or you take any shift or at any other index, right? So if you have at t1, by choosing this different s, I should be able to get all other possible indices also, right? So what does this means? Then basically the CDF of all the random variables are the same, right? If this stationarity definition has to hold for every possible n and for every possible n, so this has to hold. So for every random variable has the same CDF. Is this clear? Why this should be true? So if every random variable has the same CDF, then what does that mean? In terms of the mean, will they have the same mean? All of the xt's. So then mu of the process xt will be like something like mu x only, right? It does not depend on t. What was t here? The indices. But what we now said is the CDF is going to be the same at any index we are going to look at. That's the meaning of this condition. Because of that, the mean at any of the random variable at all the indices is going to be the same. Okay. So mean is constant. So remember that the mean of a general random process need not be constant. It is a function of indices, given index. But if it's a stationary process, it does not depend on which index you are looking at. It is going to be the same for everybody. Then now let's look at the covariance. Okay, maybe then like let's say before that. Now let's apply this the same thing for n equals to 2 case. What that means is now f of x2, x1, t1, x2, t2 is equals to f of x2, x1, t1 plus s and x2, t2 plus s. Right? Now the claim is, if you are going to look at any two pair of random variables, their joint distribution is going to be the same for any pair of random variable. Is that true from this condition? Shifted by the same amount. Shifted by the same amount. So take random variable at t1 and t2, look at their CDF. Now what we are saying is, you shift both T1 and T2 by the same amount S, then their joint distribution remains the same, right. So that is what this condition told us. So because of that, if you take the two random variables and shift by the same amount, the distribution is going to be the same. Now because of this, what does it say about my correlation? Are they going to be the same? If I am going to shift two random variables by the same amount, then their expected value should also be the same, right? Why is that? Because these two have the same joint CDF by definition. If the CDFs are going to be the same, then the expectation is also going to be the same, right? So then what it means, if I am going to look at this random variable joint distribution and the shifted version of them, it does not depend on what is the amount of the shift, but it may still look at what is this two pair of random variables you would be looking at. Suppose you change T1, T2 to some other value, that correlation may be different. But if you, what it is just saying is, you are looking at this T1, T2 and other two random variable which are just shifted versions of these two, then the correlation is going to remain same. So suppose, let's say this is T1 and T2. You shift both of them by the same amount. Okay, so whatever this delta time difference is there, here also the same delta time difference is there, right? It is just like both of them have been shifted by some amount S. But what we are just saying is, this shift does not matter. Then what should be the only thing that should be governing this covariance? The only thing that should be governing this covariance is this length of this interval, right? So R of x1 at T1 and T2 should be simply, I should be able to write T1 minus T2, or if let's say T2 is going to be larger, we will just follow this convention. It only depends on the length of that interval rather than by what amount these random variables are shifted. So because of that, here also the shift is the difference in this interval, in this time T1 plus S and T2 plus S is again going to be T2 minus T1, and that is also the same here. So this correlation, autocorrelation function is only functions of the length of the interval of these, of the at the point where these indices are taken. Okay, fine. So if you go on, I just did it for n equals to 1 and n equals to 2, right? You could go on doing this for any number of n, right? You can go and do it for n equals to 3. That means if you take 3 random variables and shift all of them by the same amount, then then it should be the case that x of t1, x of t2 all the way up to x of tn should be same as expectation of x of t1 plus s, x of t2 plus s all the way up to x of tn plus s. So stationarity is a very, very strong property, right? It makes the process kind of shift invariant, and again the joint statistics of any order is going to be independent of the shift. So we are going to say the means or the values involving only single random variable as the first order statistics, like for example mean we have already defined. So when we are going to look at two random variables, let's say xt1 and xt2, t1, t2 are two time indices, we are going to call this as a second order statistics. So here it is basically saying this is the like nth order statistics, right? Nth order statistics here is shift invariant. So stationarity is basically saying that my nth order statistics are shift invariant, and this should be true for n equals to 1, 2 all the way up to infinity. So this is a much stronger property. So what
was the significance of the second order process for this? Why did you mention it specifically here?
the second order random process?
Yeah, was that it's not specific to this discussion, right?
Okay. So what is the second order statistics? We said that expectation of t is going to be finite for all t, right? Here you could as well choose xt1 equals to t2. In this case you will fall in that case, and we need it to be finite. Okay. So as you see, the stationarity is a much stronger property which requires all order statistics to be kind of shift invariant. Instead of that, one can look at a slightly weaker version of this stationarity called as Whiteson's stationarity. What Whiteson's stationarity asks is only shift invariance in the first and second order statistics. It don't care about higher order statistics. Okay. That is, it wants that this means to be shift invariance mu at index t is going to be the same as mu at index x plus t. That basically means that my mu x is constant, right? This is going to be the same for all possible indices. And then it says that the correlation is again shift invariant. So that means, as we already discussed, this only depends on the length of this interval. So as long as you take any two random variables that has same that are separated by the same amount, then their cost relation is going to be the same. Okay. So basically Whiteson's stationarity is only restricting this condition to be hold only for n equals to 1 and n equals to 2, whereas stationary wanted it to hold for all n, all possible values of n. Okay, fine. So because of this property that my autocorrelation here only depends on the interval of the two, the difference of the indices rather than the actual values of the indices itself. Often it is given in terms of a single random. Often like you can write it as a function which takes only one argument. So here it is given, it is taking two argument, right? But two argument is essentially translating to only difference in this two argument. That means I can as well think of it is a function of a single random variable, sorry, a single argument. Okay. So if I define a process, if I say that I have a random process x with mean constant as mu, and say that its autocorrelation function is r of x tau, where tau is just a single variable, then it should be by default will take it as Whiteson's stationary random process. Okay. So let me just make this more clear. So we will just say sometimes if you say that x of t equals to r, has same mean mu x for all random variables with autocorrelation. So then we also already take it as like we understand it as denoting a wide sense stationary process. Okay. So note that even for the stationary case, my R function here, autocorrelation function, is again only depends on a single random variable, right? Sorry, single argument here, because it just depends on, but it also, for that I also need to ensure that for n greater than 2 also all these conditions hold. But if I just state only talk about the mean and autocorrelation function, and further I say that the mean is a constant or the same for all random variables, and that its autocorrelation function is just a function of a single variable, then we understand that this is already indicating a wide sense stationary. This is just like convention. Okay. Yeah. No, it does not matter which T1 and T2 you are talking about, right? So for example, as I said here, you have T1 and T2 here, and you have T1 plus and T2 S here. If you look at the correlation of these two random variables, they are going to be the same. It just depends on this interval. Yes, it is going to change. So suppose now let's say you have another T3 here, and now you are interested in correlation between, so this was let's say called delta, and let's call this as delta 2. If you are going to look at the autocorrelation between T1 and T3, it is going to be a function of delta 2 now, right? So and similarly, so here also if you know this is like T3s, and the autocorrelation of T1s and T3s is going to be the same as R of delta 2, because what matters is only their separation. Where they are, I mean with the same separation, where they are it does not matter. No, it is not. So okay, let me say, if you want to calculate autocorrelation between two random variables, what you are going to tell me is their indices, right? All I need to know is the difference in those indices, then I already have autocorrelation value for your two random variables. For example, as I said, if you want to compute autocorrelation function of at index 5 and 10, okay, it needed all I need to tell you what is the autocorrelation function value at argument 5. So and if you have another set of random variable, two pair of random variable, one at time index 4 and another at time index 10, what is the value of the autocorrelation function I need to give at which argument? 6, right? That's the only thing matters, and I am going to give you this value for all possible values. Okay, so this is for all possible values of indices. So I just need to, that is why this is a function of single random variable. One last thing I want to mention about this is, in the last class so suppose if I say a process is stationary, does it already means it is wide sense stationary? It is true, right? Because wide sense needs only a small weaker requirement. It only needs this CDFs to be invariant in shift only for n equals to 1 and 2, but whereas stationarity needs for all n. Now is the other way direction is also true. Is white sense stationary implies stationarity? Not necessarily, right? Because stationary is a much stronger condition. But as now we will see that if I have a Gaussian random process, even white sense stationarity implies stationarity. Okay, let's see why is that. So, do you recall what I mean by a Gaussian random process? So, Gaussian random process is if a random process is such that if all its random variables are jointly Gaussian, then we are going to call that as a Gaussian random process, right? Okay, now let's see. Suppose let's say I have a Gaussian random process which is white sense stationary. Okay, let's say it is white sense stationary. Okay. Now I know that if it is white sense stationary already, so what are the other things now? If it is a Gaussian random process, it is necessary that each of the random variable at any of these indices is again Gaussian distributed, right? Now I am further assuming it is white sense stationary. That means each of this Gaussian random variable should have the same mean, right? So we know that x of t for all is Gaussian distributed. Okay, and now we know that all this mu t has to be the same mu for some mu. That is the thing that is coming from your white sense stationary, right? Because this mu t is independent of mu. And now further, so another thing here, if you look at this correlation, what about the covariance? This covariance is again a function of the difference in T2 minus T1 only, right? So I can also write covariance to be T2 minus T1. So just verify that. Now what about the covariance between two random variable xt1 and xt2? We have already said that this is nothing but covariance of T1 T2 by our definition, and this is going to be covariance of T2 minus T1. What is that? So by our white sense stationary definition, we already know the means are going to be the same for all of this Gaussian random variable, and this covariance is going to be just depends on the difference in the length of their interval. Now let's look at any n random variables. Now I am interested in, now I want to go from n equals to 1, n equals to 2 to any n, and let's say n random variables at t1, t2 and tn. Okay, and this t1, t2, tn random variable, now I want to look at their distribution. Okay, and their distribution is what? We already know what is this distribution, right? Its distribution was defined in terms of the mean vector and the covariance matrix. So what is the mean vector here? The mean vector is simply mu, 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 right, everywhere, because each of this random variable has the same mu. Now what is the covariance matrix for this? The covariance matrix for this is covariance of T1, T2, covariance of T1, sorry, T1, 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 T2, and covariance of T1 and T2, and then covariance of T and Tn, covariance of right. The joint distribution of this n random variable depends on the mean vector and the covariance matrix, right. Now if you look at each of this term in this covariance matrix, this covariance, each of this term only depends on the difference of these two terms, right, nothing else, okay. So now if I am going to, and what we know how to define the joint distribution of this set of random variables, right, we in terms of the mu and k, we already did it in the last class. Now suppose if I shift each of these time indices by some amount, the mu vector is not going to change for the random variables at these time indices, right, because it is going to be the same for irrespective. Now what about the covariance matrix? Does it depend on this shift S? No, right, what? Because the difference, if you just take T1 plus S and T2 plus S, the difference is only T2 minus T1 now, the S has no role in this case. So as you see that the joint distribution is now independent of the shift we are going to look at, right, and that is what, and this is true for any n. So then what does this mean? Our requirement of stationarity satisfied, right, the PDF is going to be the same. If the PDF is in this case is invariant, that means also like CDF can argue that CDF is also invariant, right, of the shifts, then my stationarity property is satisfied. So for a Gaussian and a process, White's-Son stationarity implies stationarity. And anyway, this other way is always true by default, right? But if you have a Gaussian random process, the weaker notion of White's-Son stationarity already implies the stationarity. Okay. Okay, so just one last thing about this is, so far we have been talking about one random process, right? I mean, so it may happen that you may have to deal with multiple random process. So let's say this is my one random process, and this is my another random process. Where all the random variables are defined on the same probability space, right? So when we say the random process, we mean that all these xt's are defined on the same probability space, right? So now let's take another random variable, another random process where each of these yt's are defined on still the same probability space. Now when we have such things, maybe you may still want to define what is a correlation similarly and covariance in this case, right? So in this case we are going to define Rx y at point S of t to be expectation of the first random variable computed at time index S from the X process, and the second random variable is the coming from the second random process at time index t, and this is called cross correlation. And similarly, you can define cross covariance okay. This is and one last thing, if xy xt is only y, then we call x and y are jointly bisexual. Okay. So this is just like an extension of notion from one random process to multiple random process when we have to deal with. So it may so happen that for example, let's say you are dealing with the stock exchanges at every day, the maybe Bombay Stock Exchange, how it is varying every day, and so you are going to model this as a one random process, and maybe you feel that weather has implication on the Bombay Stock Exchange. So then you may want to model another process which is like a weather on each of these days as another random process. Okay, so then you may want to see like how they are correlated, what is the covariance between them. So each of this process could be corresponding to some aspects of something that you want to model, like outcome of experiment which is like many indices. So that one experiment, and if you have another experiment similarly which has many indices, if you want to like understand how one has influence over the other, or what is their like correlation or covariance, you want to look for all such properties.